Hi students. Okay, so we're more than halfway done now, and we begin this chapter and this video by introducing hypothesis testing. That is our first step into introducing inferential statistics. That is where we start comparing samples to populations and we start testing conclusions and hypotheses that let us say whether a sample is the same or different from the population. Next, we'll compare sample to sample, but that's going to be the next chapter and chapter 10 as well. So if you've ever asked questions like, does a particular treatment work, or does a particular product work for you? In medicine, they do hypothesis testing to test whether certain drugs or vaccines work to make people better, to treat diseases and prevent illnesses, and so on. The same question can be asked for things like, hey, does sleeping more hours at night or does sleeping earlier at night help people do better in school or make people feel healthier or reduce stress or other things like that? Or you could even ask whether a certain program or a certain course or a certain tutorial or a certain service is going to help you in your courses. So whenever you ask a question, really, whether it's about whether something works or whether something's different than another, we are engaging in one type of hypothesis testing or another. So hypothesis then is the thing we're going to test about a prediction that we want to see whether the evidence supports it or not. And in this class, where we analyze behavioral data, we're going to use that data, whether it's grades or sleeping hours or some measure. It could be of your heart rate or blood sugar levels or something. We're going to see if there is a difference between the sample, and especially a treated sample, versus the population that already exists. So there are 6 learning outcomes for this chapter, and those are the 6 things we're going to help you make sure you know what to do. So these outcomes are: 1, we're going to make sure we can describe the logic of hypothesis testing. And there are 5 steps here. 4 plus the conclusion that you're going to state based on the evidence that you found from your sample data and sampling distribution, and then you test that, and then you make a decision. And we'll go through those 5 steps, which also includes, is our second learning outcome, stating the hypothesis and locating the critical regions. Our first step is to actually say, well, if there is no difference, or if there is a difference. Both of these are hypotheses in themselves. So each of these is one hypothesis. If you say no difference, that's a null hypothesis. If you say yes difference, that's an alternative or research hypothesis. And for us to make an informed decision based on statistical data, we need to be able to locate a critical region in the sampling distribution. That's the distribution we're going to use to make our comparison, a distribution of means. And we're going to see whether this mean from that sample is far enough away from the population mean for us to go, yeah, yes difference or no difference. So those would be steps 1 and 2. Next, we're going to conduct a z-test. Well, we're using a z-test here because we're working with situations where, for now, we know the population distribution, including its mean and standard deviation. Once we have compared the sample mean against the population mean in the sampling distribution, and we can say whether it's far away enough from the population mean for us to say there is a difference, whether it's outside or within the critical region, then we make a decision to say whether there is yes difference or no difference. When we say yes difference, we are rejecting the null hypothesis, and when we say no difference, we fail to reject it. And we'll explain that as well. So that would cover our first section, I think. Next, we'll go over defining and differentiating different types of decision errors we can make. A type 1 error and a type 2 error, where, for example, if you decide to say yes difference and reject the null, but it turns out during your test, statistical test, there actually was no difference, then that's one type of error. Or if you say no difference, but you actually say that and then there actually is a difference, then that's another type of error. And we'll learn to be able to define those types of errors and distinguish type 1 and type 2 as well. The fifth outcome is we want to describe effect size and compute one measure of effect size, that is Cohen's d. This outcome only applies when we decide there is a difference. Again, it could be an error, but once we have made that decision based on the evidence that the sample mean is within the critical region where we say we will reject the null and say yes difference, then we measure the effect. How far away is that sample mean away from the mean? What size is that effect? And the effect here is going to be commonly referred to as the treatment effect. And number 6 then is we're going to apply all the outcomes we've learned and start making different kinds of hypothesis tests, like whether we're just looking to see if the sample mean is just different. It could be above or below the mean. Or if we're looking at whether the sample mean is specifically above or below the mean. This would help us determine whether we want to do a one-tailed test, that is a directional test here, or a two-tailed test where it's bidirectional or non-directional because you're not looking at one particular direction and you're just looking for a difference. And we'll distinguish those as well. So those are our 6 learning outcomes. At this point, before I go on, this is where the course can get harder. This is where the course would have specific steps for hypothesis testing, and this is where the course starts really going into the research aspect, where we actually have research questions in the form of hypothesis that answers those questions, and we're going to test those answers. Again, generally, the answer is going to be yes difference, the alternative or research hypothesis, or no difference, the null hypothesis. So success in this chapter and for the rest of the course involves describing, reviewing, teaching, and testing yourself in these hypothesis tests and doing hypothesis tests in the practice questions. So make sure you have built a strong foundation in terms of your descriptive statistics, so your central tendency, your variability, your z-score, your probability, and that sampling distribution. Those are all the skills you're going to need. So that's what the next slide is about. The tools you're going to need at its core. You're going to need z-scores for this chapter because we're working with z-scores, comparing samples with populations. And you're going to need for sure the distribution of sample means, or the sampling distribution of means. So chapters 5 and 7. You're going to need chapter 6 as well because you're going to work with probability, but chapter 7 covers that anyway and assumes you know and you can practice that. So let's begin. When we introduce hypothesis testing, it is the most commonly used procedure in inferential statistics. That is, well, how are we going to answer research questions using behavioral data, using surveys or experiments or some type of study that for us we can say, oh yeah, there is a difference, or there is a correlation, there is some kind of relationship. And so we're testing these hypotheses and answering research questions based on the ones that we just talked about. And you can think of your own too. We also use hypothesis testing as a statistical procedure, as a way for us to see whether the sample is representative of the population or whether it is different from the population. So the logic of hypothesis testing goes like this. Well, first, you're going to need to state a hypothesis. Actually, you're going to need to state a pair of hypotheses. Usually it would be in the form of, well, you're going to answer a question, is the sample, usually it's the treatment group, which is a treated sample, whether that is different from the population. And if it is different, then that means that treated sample that receives some type of treatment, whatever it is, that treatment has some effect on that sample. And if you have a way using statistical procedures to say, hey, if that treatment works for that sample and that sample is big enough and the difference is great enough, then we can say probably that this treatment works, and you can give this treatment to other people from that population and go, well, yeah, it's going to work for them too. So in many ways, hypothesis testing is not only practical but important because these are going to deal with real life things. Again, it could be medical, it could be academic, it could be social, political, whatever. And this is the tool we use under the scientific method. We predict the expected characteristics of the sample based on the hypothesis. That is, we're going to use means, expected values. So we will be working with the population mean, which we can calculate or determine by using the sampling distribution of means. We're going to work with also the sample mean that we collect from actually collecting the data, and we're going to compare the two. And what we're going to need to start, well, we're going to need the sample. Again, if you were able to produce some treatment and you're able to test everyone, you wouldn't necessarily need inferential statistics. You'll just do it and give everybody the treatment and see, well, how many people out of the entire population changes. So that would be more descriptive at that point. But still, we would grab a sample first and test the sample. Then we compare the sample data with what we predict from the hypothesis. So here is the prediction. And you may remember this, or you were going to learn about this in a research methods class. There is something called a confirmation bias. That is, in using the English language, a common saying might be, people, whether it's, scientific research or just everyday life or teaching or learning, we often like to hear what we want to hear or what we expect to hear. And when we are told otherwise, we're given some result that's not something we expect, we might not be the first to say, yeah, oh, that's true. So this is why it's a confirmation bias. We tend to look for things that agree with our assumptions about the world. And so in hypothesis testing, when we test a hypothesis, we're more than likely going to expect a difference, especially if it's some treatment that we made or something we are testing ourselves. So rather than looking for the research hypothesis and saying there is a difference, we want to account for this bias and say, oh, instead of looking for some difference, we're going to predict that there is no difference. And if the evidence is strong enough, then we can say, okay, yeah, the evidence says there is a difference. So an example of this would be in most courts of law, not all courts of law as it should be, that you're innocent until proven guilty. That means, well, no matter how serious the crime is, we start with the assumption that the person is innocent, and we let the evidence speak for themselves, as in proving that person is guilty beyond any reasonable doubt. So that kind of process then applies to hypothesis testing. We want to use sample data and the evidence to say whether that data supports a hypothesis, is consistent with it, then we fail to reject it, or if that data shows extreme values and is not consistent with a hypothesis that is consistent with the population distribution or the expected value of the population distribution, we'll reject the hypothesis. So a quick picture of this will be like this. Here we got a sampling distribution of means, which is used to approximate or represent the population. And this particular distribution we're going to call the null distribution because, well, it's supposed to represent the population without treatment. So in that distribution, there will be no difference, no effect. It has its own standard error, it has its own mean, and that mean is the same as the population mean. And then we can measure those in terms of standard deviations and z-scores. And so if we set some region and say, okay, maybe 2 or 3 standard deviations away, let's say 2 for now, is on either end of this plus or minus 2, it's going to be about somewhere between 2.25%, 2.27 or something like that. So that means on either end, only 2.27% of the entire population on each end is going to get that sample mean. So if your sample falls somewhere over in one of these regions, if you're just looking for a difference, then you go, yeah, I'm going to reject this. The evidence is telling me to go, oh no, and I'm writing right H0, that's the null hypothesis. That means no difference. So the sample mean is far enough away from the population mean for me to go, yeah, there really is a difference. I'm going to reject the hypothesis that there is no difference, that this null distribution says, oh, the null is true. But the evidence shows the sample mean is far enough away that I go, no, I'm going to reject the hypothesis. So here's an example of this. So in this slide, we see some known population before the treatment. And we grab a sample. Again, if the treatment was big enough and we have enough resources, we could do it for everybody, but we really can't. So we grab a sample, give them the treatment, and see if that treatment makes the sample different, as if it's from a different population. So if the treatment works, then the average for everyone that takes the treatment would be different. It could be higher or lower, so it would no longer be 80. It would be far enough. It could be 85. It could be 90. It could be 100. It could even be 82. But notice here that there is a standard deviation, and we need this because now we know what to expect in terms of difference. Hey, if any of these numbers I mentioned here so far, they're still less than, well, except for 100, they're still within 1 standard deviation away. Well, that's really not extreme enough, because if you remember, in a Z distribution, only 34% of the population is 1 standard deviation away from the mean. If you count the other half, then 68 or so % of the population is within 1 standard deviation above and below the mean. So maybe the population mean, instead of 100, it could be 110 or 120, where you start looking at maybe 2 standard deviations or more, 130. So then we go, oh yeah, wow. Hey, the score is really extreme now. It's 130 something or 120 something. It's more than 2 standard deviations away, where 95 or so % of the population would have scores between, in this distribution, 2 standard deviations away, 40 and 120. So anything more than that, you might be inclined to say, yeah, that is from a totally different population. This is where you would think of examples where, somebody really changed, or an entire group of people really changed, or a particular treatment is effective. The vaccine works, people no longer get sick. The survival rate jumps from, or the death rate, for example, jumps from 90% to 10%. That's a big difference. Or your average for the class, if there's some sort of tutorial that changes from, 50% to 70% or even 80%. That would be really high, but yeah, they will say that's a difference. And that's the thing we're trying to test here. So conceptually then, this is how it works. Again, we don't have a distribution graph this time. We're not doing these pictures at the moment, but the concept works like this. We have a known population that is not treated, and we have a sample here that is not treated either. But if we treat that sample, the sample becomes treated, a treated sample, and we're trying to see then if this treated sample is still getting scores of some kind that is the same as or within the expected range of the population distribution, or is it far enough away from that for us to go, yeah, this is going to be from an entirely different population. So again, for example, using your class, if the class average for this stats class so far is Psych 218 is somewhere between 60 and 65. If this class gets an average of between that, could be 62, then you go, yeah, no, it's from the same population, nothing's really different. If it was 66, you go, well, you know, it's a little higher, but it's still really close, right? Again, you need the standard deviation for us to work out how far is too far. But let's say, for example, if one standard deviation is 10, then if this class scores a 75 average for the same size, like 34 people, then you go, yeah, something's going on. Whether the students are performing better because they study harder, or there's something else going on. You can think of other reasons, but it is starting to look different. I mean, the further you go, the more likely you're going to say, yeah, that's different. Like, let's say 85. The most obvious one is, well, if somehow I just pass everybody. Well, I'm no longer marking your stuff. I'm just giving everybody 100%. That's really different. The interesting stuff is where it gets to a point where it looks far enough away, but you're going to need a systematic way, a procedure of doing it using statistics for us to go, hey, the data shows there is a difference, or the data shows there isn't one. I'm going to either reject or fail to reject that null hypothesis. So here are the 4 steps plus 5. And the 5th one is you state your conclusion. But your first 4 steps are going to be the key. So for every hypothesis testing, your 4 to 5 steps are the same. And the steps go like this. First, you state the null hypothesis and the research hypothesis. Then you set a criteria for your decision. That's where you go, oh, in the sampling distribution, what value should I set for the sample mean to be far enough away for you to go, yeah, there's a difference. I'm going to reject the null hypothesis. Step 3, and notice the order here. First, you state your hypotheses. There is a difference, or there is no difference. You're going to need to do both of these. Or if there is a difference, you might specify, is it an increase or a decrease? For the null hypothesis is relatively straightforward. It's the opposite of the research or alternative hypothesis. If you say there is a difference, you go no difference. Null means nothing, 0. No difference. Or no effect, because the effect then is supposed to create some kind of difference. Okay. And we'll talk about directional tests as well, where, for example, if you're looking for an increase, well, if the, like, for example, some tutorial or some tutor service is going to improve your grades in this class, but actually the tutor is making your grades worse, well, there is a difference. It could make your grades even drastically worse, God forbid, but would you still reject the null? Or would you say, well, no, it's not giving us what we want. That is increasing our scores far enough for us to go, yeah, this is effective. So we're going to look at that as well. Notice the order again. You state the hypothesis first, and then you set your criteria for your decision before you even collect data. This is an example like where you buy fire insurance before the fire happens, or you plan to do something first, like, oh, I plan to study for this test, or I plan to do my assignment before the due date. You set your hypothesis and criteria first, and then you collect your data, and then you calculate your statistics. It would be illogical. It would not be ethical if you collect the data first and then go, oh, wait a minute. I look at the data, doesn't seem to be a difference. I'm going to change my hypothesis. Or, oh man, that data looks really, really close to the population. I'm going to set my criteria a little thinner. Like, no, you need to set the criteria first, and we're going to show you how to do that before you collect the data. In this course, the data is given to you. So step 3, you would calculate the Z-score and do mostly this using the data that's given. In other courses, you might be given raw data that you would compile from the sample and go, oh, this is the sample mean, this is the sample variance, this is the sample standard deviation, this is the pooled variance, and so on. But for this particular chapter, your data is going to be given to you in some form. The sample mean, the population standard deviation, the population mean, so you just calculate standard error, you know what the the mean of means is, and then you decide from there. Finally, you look at your computed statistic, compare it with the critical region and the critical value, and then you go, oh, if it's far enough away, I reject the null. If I see it as not as far as the critical region, then I fail to reject the null. And then the last step that's added here, well, you state your decision. Like, okay, because we rejected the null, we would conclude based on the evidence that we found that, there is no treatment effect, or there appears to be some treatment effect, something like this. So we're going to go through the steps next. So step 1, we state the hypothesis. Here again, when we state the hypothesis, we were really stating 2. And these are the 2 hypotheses. The first one you state is the null hypothesis. Null means 0, nothing. So here the null hypothesis means no difference. The alternative hypothesis, or the research hypothesis, the thing you're asking about, and this is the answer to that research question if there is an effect, you're saying yes difference. So here I put a difference. You can think yes difference. Okay. So again, null hypothesis means no difference, no effect. Alternative hypothesis means yes difference or yes effect. Yes, there is some kind of effect. The notation for the null hypothesis is H, capital H, for hypothesis, and then 0, which is read as not, as in like not for 0, for the null hypothesis. Again, the sentence says no change, no difference, no relationship, no effect in the general population. Here it should read alternative hypothesis, and that says, well, is H1. Sometimes you might see it as HA subscript, and that states that there is a change, there is a difference or a relationship in the general population. So I'm just going to change that right now. Alternative hypothesis done. Once you've stated your hypotheses, then you would set your decision criteria, or specifically a critical region. Here is use criterion because you have just one criterion. So here's how you do it. First, you would need a sampling distribution. So here, the distribution of sample outcomes, you're working with the sampling distribution. So you would have a sampling distribution of means that assumes the null is true. And then it has its standard error, and then its mean of means. And then these are sample means in here. That assumes that there is no difference. It comes from the original population with no effect. And then you decide at this point, how far is too far? So let's say, for example, we want 2 standard deviations away, above and below the mean. So if the sample mean happens to be less than 2 standard deviations above or below, we would say, yeah, you know what? We still expect that. That can still come from the population. But if we see something from a sample and the mean of that sample is further than 2 standard deviations away from the mean, then it's very unlikely. Because remember, each of these regions is like 2.25% away. If these are 2 standard deviations away here. So this is -2 for Z, and then for Z, then here would be +2. So if the score happens to be within this critical region, and this is something you draw, by the way. So this is step 2. So this would be your critical region right here, like this. See? So you have within anything within that outside that critical region that is closer to the mean, you'd go fail to reject the null. And we're going to discuss why we use specifically fail to reject and not accept the null also. And so anything that is more extreme than that, we can clearly say, yeah, we're going to reject that null hypothesis and say there is a difference. So that's what that means. So the critical region would be values that are more extreme than our region of expected values. Again, if we use 2 standard deviations above and below the mean, then it's about 95%. A bit more than that, actually. Of the entire distribution of sample means, it's going to fall within that region. But everything else above or below that, it's going to be that extreme, close to 5% that's left. You can set the critical region however you like, but generally you want something that reduces your chances or probability of saying there is a difference when there really isn't. So that's one type of error. We're going to talk about that as well. But the boundaries you set here to help you determine and decide whether you want to reject or fail to reject the null based on the sample mean and where that is in the sampling distribution, that's the critical region that you're going to set. And that boundary, that critical region, is called the alpha level because, that is where you decide to say there is a difference. And if there happens to be no difference, it still comes from that population. Even if the value was so extreme, then it would be a wrong decision, and that would be a type 1 error. So the probability of a type 1 error then here is about 5%, and that's value as noted as alpha. So here's a picture that describes this. So I just drew one in the previous slide, but here's one in the full slide. Here again, this is your sampling distribution. If the null hypothesis is true, again, this is a distribution of sample means where the means are here like this. And then these are means collected from the population where there's no treatment effect, that there's no difference. So again, you can write something like the null is true. Here is in short form with notation, H0 is T for true. Okay. The mean here is from the H0, which is from the population mean. And then here is the distribution of sample means. And you won't be using the population distribution here because, again, first of all, you can't. It's almost impossible, especially for large populations. Second, we're applying the central limit theorem with sampling distributions where there's something we can actually do with the sample that we got. And we're trying to see whether that sample mean is, extreme enough, and we're using the sample data that we got to determine that. So once we have set our sampling distribution, then we can establish our critical regions somewhere that is where the sample mean is far enough away from the population mean, where the probability of us getting those values, those means, is so low that you would say that is really different. An example of this, again using criminal cases, would be like, oh, is this person the person that did it? And let's say it was a DNA test. So usually DNA test would be something like, oh, if the DNA test shows, hey, this DNA is unique and it matches the blood or some fingerprint or some saliva sample or some skin sample, some DNA sample that says, hey, this is out of a population of 7.8 billion, like today, then, there's only like 1 or 2 people that matches. Instead of saying, oh, out of that 7.8 billion, well, 95%. So that'll still be something along the lines of at least 6 billion. So you're going to try to find that one person in 6 billion people versus trying to find that one person in like 1 or 2. So again, we're looking for that extreme value. Usually it's going to be like either 10%, 5%, 1%, 0.5%, 0.1%, and so on, depending on how extreme you want the value to be, how much you want to, or how little you want to make a type 1 error where you say there is a difference when there really isn't. So, but if that value happens to fall within that region, you would say reject the null. In this case, is a two-tailed test. You're looking for something that could be either above or below the mean. And then everything else within this point region here, again, we use fail to reject. So quickly, we say fail to reject in the region where it's within expected value of sample means because, well, unless you get a value that is exactly at the mean. And remember, we've already established in previous chapters and logically that a sample mean is never really going to be the same as the population mean. Again, you could get the same value, but the data is different. So we can't accept the null because by default, the sample mean is not the same as the population mean. We can only look at the sampling distribution and go, yeah, you can expect a value that is close to the mean, but not far enough for us to say that there is a difference. So that's why it's fail to reject, not accept the null. Some of you might read something like retain the null, which is closer to accepting the null, but it's not accepting it. It's just like, I'm just going to hold on to it. But again, what you're doing is you can't reject it because it's not different enough. It's not far enough away from the mean for us to go, yeah, there is a difference. So, for example, this alpha here, this A or Greek letter A, this is going to be our probability of a type 1 error. And type 1 error here, which we're going to discuss later, is to reject the null when it turns out when we test the when we test the sample, that the null hypothesis is actually true. That sample that you got, it turns out to come from the same population, or it turns out that there is actually no effect. But you have decided to reject it based on what you've seen here of how extreme that value is when you look at it, the sample mean in the sampling distribution. So again, the value here, this critical value that you set, determines where you place the markers on your critical region. And the points here on that sampling distribution with Z-scores, these are your critical values. In a two-tail test, you would have critical value 1, which is below the mean, or critical value that is below the mean, and another critical value here that is going to be above the population mean. And the region here that is the shaded area, these would be the critical regions. That's the probability areas. Again, in two-tail test, the area is divided into half. So here you set the alpha, the probability of a type 1 error where you reject the null when the null is actually true on the day of the test. Or at the moment when you test the data. Collect and test it. So here notice it's two tails. And so it's not 5% here and 5% on the right. It's actually 0.025, which is 2.5% on one side. And then here's the other 2.5%. Okay, so for the test we're doing right now, we're going to just look for a difference or no difference. That means it could be above or below the mean. Therefore, the critical regions would have split into two halves. One half for extreme values above the mean and one half for extreme values below the mean. And so there are two critical values, one above and one below. Here is going to be negative 1.96 and here is going to be positive 1.96 for a z-score. And so those would be your 2.5% close to exactly. So again, that would be saying, oh yeah, only 5% of the entire sampling distribution is going to get a sample mean that is either above or below 2 standard deviations away from the mean. Well, that is more than 2 standard deviations above or below the mean. Extreme values. So here's our first learning check then. We're going to focus on step 1 here. And the question reads like this. A sports coach is investigating, trying to figure out the impact of a new training program. So you can think what training programs are supposed to do. So using words then, what would the null hypothesis say? Again, there is an alternative or research hypothesis. We're practicing step 1 right now. The question is whether the training program works. And so there are two answers, two hypotheses. What would the null hypothesis say? So take a moment and read the choices. Again, I can read them for you. A, the new program produces different results from the existing one. B, the new program produces results that are just like the existing one. C, the new program produces better results than the existing one. Or D, there is no way to predict the results of the new program. So think about what the null hypothesis means and use that to make your null hypothesis. So the best answer for this question then, I just corrected the typo, that the new program is going to produce results just like the existing one. That means it's not going to change anything. That means there's no difference. That means there's no effect. That's the null hypothesis. So that means the whatever sports team that is, be it a football team or a soccer team or some large team sport, or it could even be tennis team, doesn't matter. So looking at all the results that they had so far, maybe they tried, year after year trying to, win a tournament. So there's a new training program. And that tournament measures, the team's results by scores, and they fail to win or they fail to meet a certain marker. And so the new program comes in, they try to see if they improve the scores, and then it turns out the scores are just exactly the same or very close to exactly the same. So that would match or support the null hypothesis that would say, oh yeah, the program just does the same thing. There's no effect. There's no point. No difference. Okay, so question 2, let's give these a try, true, false. A, if alpha level is decreased, the size of the critical region decreases. So again, alpha level here is the probability of a type 1 error where you reject the null, but it turns out that the null is true, that there is no difference on test day. So if you decrease that probability, you want to reduce the probability of making that error, then the critical region decreases. Is that true or false? Second, or B here, the second statement is the critical regions define the unlikely values if the null hypothesis is true. Again, the area of unlikely values is going to be the region where you would decide if that sample means false. Within that critical region, you go, I'm going to reject the null. So again, is that statement B true or false? So for both of these, the statements are true. So first of all, again, if you want to reduce your probability of rejecting the null and therefore reducing the probability of making a type 1 error, then yeah, the critical regions would be smaller. And before we go into that, we can look at B as well. Yeah, the critical region is that area of unlikely values or unlikely sample means in the sampling distribution where it says, oh, if the null hypothesis is true. So looking at A then, if you need some help in terms of picturing this, let's say we have a couple of sampling distributions. And this is just one standard error away. And all of these are going to assume that the null is true. We're working with the sampling distribution here. So if we want to take our chances, so to speak, in plain English, or if we want to increase our probability of saying that there is a difference, that means we're increasing our alpha level. That means we're going to say more often with more sample means and going, yeah, that we'll consider that extreme. So for example, if we set our region instead of plus or minus 2 away from this population mean in terms of z-score, we go plus or minus 1, then the alpha regions are going to be huge. So it's going to be 68%. So you got 32 left. So it's like 16% on this side and 16% on this side. Whereas if you set your alpha here something much lower, like 2 standard deviations away, or 2 standard errors away, so then here you're going to have plus or minus 2, and this is going to be your close to 5% again. Notice it doesn't sound like that much, but yeah, 1 standard deviation is a lot of the population. Again, you can check your unit normal table for this. And finally, if you go really extreme, make it really, really small. It's like over here. I'm going to say this is like 3 standard deviations. This is going to be like 0.5% over here and like 0.5% over here. It's going to be very extreme. So this would be like 99% or so. This would be like 95%. And this would be like 68.128 something percent, about that. So again, the alpha level, as it decreases, your critical region decreases. And you can say it the other way. If I decrease the size of the critical region, if I put in really, really unlikely values, that is really far away from the population mean, then that area, the probability where we reject the null hypothesis is going to be that much lower. And again, when we reduce that probability, we also reduce the probability of a type 1 error. But also that means we're not going to reject the null nearly as often. So step 3 then here is collecting the data. Remember, we want to do steps 1 and 2 before we collect the data. Again, you can think back to the fire insurance example or doing stuff before the due date example. We want to state the rules first before you actually collect the data and make a decision. Another example, if you really need another one, is like, well, if the instructor gives you the assignment, the instructor should state the rules first. Or the instructor, shows you the course, here's the syllabus, here's how it works. Or you go to a game. You probably want to know what the rules are first if you want to win. So again, that's step 1 and 2. We set the hypothesis and set our critical regions. Then we collect our data. In terms of data collection, that is more focused in research methods for our second year level psychology courses. And for this course, for this chapter, you're given the data. It's usually just some sample mean, or you could be given a distribution of sample scores, and then you'll be asked to calculate the sample mean and other sample statistics. So those will be done. Again, the key here is the data is always collected after you state the hypothesis and establishing the critical regions, not before. Always, always, always after. So after you got your data, this will be set free at this point, no earlier. Then you have the sample statistic that you can compute into a z-score. For now, we're going to work with examples where we know the population standard deviation and the population's mean. So we can work with z-scores. In the next chapter, we're going to work with more common examples where we don't know the population parameters, like we don't know the population standard deviation, and sometimes we don't even know the population mean. So then we're going to need t-scores, not z-scores, and we're going to talk about that. But for now, we're going to use z-scores where we can make use of the sampling distribution where the null is true, where it has some standard error and some population mean, where we set our critical regions. We have stated our hypothesis. Again, the null is something, no difference or no effect, and you would write these down first. Yes, difference, like that. See? Something, right? So that's step 1, and then you do step 2, which is drawing this distribution, setting your critical regions to say whether you want to, where do you make a decision to reject the null, and where do you fail to reject. So that's going to be your steps 1 and 2 first. And it is in that distribution, that sampling distribution, that null distribution, where you put that z-score somewhere in the distribution according to that location. It could be in the region where you fail to reject. It could be in the region where you reject. But that z-score is going to tell you exactly what to do. Then, once you compare your test statistic, your sample statistic, which is your z, and you compare that with the critical value. So, for example, if we have a sampling distribution that is now the null distribution, let's say we assume we stated our hypothesis already, so it's done. So, no difference. Yes, difference. Okay, so that's step 1. We do that first. Step 2, we set our region. Okay, let's say we set our alpha at 5%, plus or minus. So this would be 2.5% on one side. Again, when you do a two-tail test where you're simply looking for a difference, the alpha is split in half. And then you would make your critical region anything that is above, greater than 2 standard deviations away. Here is 1.96 specifically in terms of z-scores. So if you happen to get a sample mean that when you transform it into a z-score is like, less than 1.96, away from the mean, it could be +1 or -1, but the distance is less than 1.96 away. Then you're in the region where you fail to reject. If you happen to get a z-score that is translated from a sample statistic, a sample mean, that, the z happens to be like 3 or -3 or 2.5 or -2.5, anything that has a greater distance than what you set as your critical value that dictates your critical region, you go, oh, I'm going to reject it. So you might write something like this. If the z is within 1.96, then I'm going to fail to reject the null. If the z-score is above 1.96 or it's less than -1.96, then you're going to reject the null because that value is really extreme. Okay. So then we make our decision. Let's say, for example, we found the test statistic. Okay, the z here, and this is our z observed. So that's our observed value. And that is that greater than our critical value? Well, let's say, for example, it was 2.5. Okay, so 2.5, yeah, that's greater than our critical z value, which we'll label as z crit. And then, yeah, the critical z value here is ±1.96. Well, it's bigger than the positive 1.96. So therefore, we do the decision that we set before, the rule. We follow the rule and we reject the null. And that's our decision. So those would be the 4 steps that we need to do. And right now we're just going through the steps. When you work with the worksheets, you can write down those steps and follow those steps and practice for yourself. It's important that you practice these 4 steps to really start to review and apply hypothesis testing in this course. So here's an analogy then of hypothesis testing. Again, we talked about jury trials and criminal cases along with medical cases and your studies and whatnot, but this time we're going to use a jury trial. Again, you might remember me talking about the whole innocence until proven guilty thing. This is the analogy we're going to use. So in a jury trial, again, somebody goes to court. The assumption that the courts go by is the person is innocent until the evidence proves them guilty. So the null hypothesis then, at least for the defendant, is going to be, well, the defendant pleads not guilty. Of course, if you study law, you know that defendants can plead guilty, often for a lesser charge. It's usually when the defendants know they did it and they don't need to go to trial because the trial is just going to prove them guilty. So the defendant would plead guilty for that case. But if the defendant decides to plead not guilty and that defendant goes, no, I didn't do it. When people ask them, did you do it? They go, no, I did not. That's the null hypothesis. I did not do it. I'm not guilty. So we set the critical regions then. So this would be step 1. Step 2, well, we gotta decide, well, how much evidence do we need in the court for the jury to say, yeah, this person is either innocent or guilty. The jury has to decide. So this is where the jury would go, okay, well, how much evidence do we need here? What are we looking for? So in our hypothesis testing, we would set our critical regions for us to say, well, what values would we consider as unlikely? What sample means would we go, that's really far enough away, like that where only 5% or 1% of the population of means in the sampling distribution would go, yeah, no, it's really unlikely. So again, if it is likely, as in this is not like likely to be guilty. This is where it's like the evidence shows that the defendant is not there, or the defendant is no different from everybody else who did not commit the crime. So the defendant here is, as the slide reads, likely to be innocent, therefore not guilty. However, if the evidence shows, hey, this defendant here, this person, the suspect is, he's not like he or she is not like everybody else. I mean, he or she really did something, and the evidence really shows that this person did something to commit the crime. So this person would be unlikely to be innocent, and very unlikely, then that person would be guilty. We have this, the jury would decide the rules before they collect the data, before they go to court and look at the evidence. So the data collection bit here would be like going to court. They have lawyers and they have witnesses. They give the evidence. And so the court then looks at the evidence and tests that plea. And so they compute the test statistic. Here is they go, okay, look at the evidence. Does that evidence show the defendant is likely to be innocent or unlikely to be innocent? And then they decide at that point. If the evidence shows the person is unlikely to be innocent, then the jury rejects that plea, rejects that null hypothesis, and goes, defendant is guilty. If the evidence shows that the defendant is likely to be innocent, like defendant didn't do anything, then the jury would not be able to reject the plea, that is not able to reject the null hypothesis, and then go, yeah, the defendant, we wouldn't say that defendant is not guilty. So this part here is step 4, the decision-making part. And so that's what we're going to do. That's the logic of hypothesis testing. And the logic is important here, because without these steps, the only thing, mathematically speaking, that you got is z-scores. That's it. But without a critical region, without understanding why you set that critical region, without understanding what hypothesis you're testing and what questions you're answering, all you got is a z-score. And you can't make inferences because you have no answer to no question. So there's no research that you're doing. And so hypothesis testing is used for research, where we ask questions about things that happen in the world that we do. So whether it's a jury trial or a vaccination or some medicine or some training program or tutorial program, we often ask the question whether it has an effect or not. And these are the 4 steps we need to test that using behavioral data. So this is our last learning check of this part of the chapter recording before we go on to the next part. So question 3 here, it's 2 true-false statements. A, when the z-score is extreme, it shows that the null hypothesis is true. True or false? And B, a decision to retain the null hypothesis means that you prove that the treatment has no effect. Here, read retain as failing to reject the null. If you answered false to both of these statements, you'd be right. First of all, if a z-score is extreme, that means the value is really far away from the population mean. Which also means that the value is unlikely to be part of the population. So an extreme z-score could be like 3 standard deviations away from the mean. And so therefore, it would reject the null and say stuff like, yeah, it's very unlikely that the null is true. For B, your decision to fail to reject the null, where some people would say retaining the null but never accepting it, because again, the sample mean is never the same as the population mean. Even if it's the same value, the data is different. Then you prove that the treatment has no effect. No, you haven't. Again, it's based on what we said. You fail to reject the null, and the mean could be from anywhere within the region where you fail to reject, especially if you want to be cautious about rejecting the null in the first place. So you want to reduce type 1 error, but at the same time, you could be failing to reject a whole bunch of values which can be quite different. You could have like 1.9. If the critical region was 1.96, is still below the critical value in the positive direction, so you fail to reject it. I'm going to write it above this time because we ran out of space. So here is reject. Here is reject. Anything that is greater than 1.96 standard deviations, standard errors away from the mean. And so you got this whole really big 95% fail to reject region. But the mean could come from anywhere within that region. And remember, the sample mean is never really the same as the population mean. So you haven't proved that the treatment has no effect. You're just deciding to not reject the null because you can't, based on the decision rules that you've made. So that's it then for this part. So the next part, we're going to start talking about the different types of errors you can make in hypothesis testing. That is type 1 and type 2. We talked about type 1 already, where it's labeled as alpha. That is the probability of a type 1 error where you reject the null when the null actually is true. So you're going to say there is a difference. We decide to say there is a difference based on the evidence, but it turns out, there actually really isn't. The other error then logically would be to say there is no difference when there actually is one. So that's type 2 error. So until then, try a couple things. One, if this is totally new to you, the first thing you want to do is write down this checklist found in slide 8, the steps themselves, so that when you practice your questions, you know what you need to do each time. You might not understand it, but at least you know. Next then is, for each step, make sure you're able to do those steps as you understand and apply by describing those steps and replicating it. So in step 1, you would write your two hypotheses, the null and the alternative hypotheses. In step 2, you would set your critical regions based on the hypothesis using the sampling distribution. Step 3, you would have some data. Here you could use some values. Let's say you can find a z-score that is below the critical value in terms of absolute distance, or you can find some value that is above that value in terms of absolute distance. So if you set the critical value of z at plus or minus 1.96, well, if you throw in a 2 point something, that's going to lead you to reject the null. If you throw in a value that is, I'll use this slide here. If you throw in a value that is less extreme than that, it could be like 1, then you fail to reject the null. Then you state your decision, step 4, and then those would be your 4 steps. So there are practice questions with these. Again, you can use your textbook, you can use your web tutorials to practice these. This first part here is, in one sense, very abstract, but at the same time very concrete in terms of steps. So make sure you know those steps, you're able to write down those steps, recite it if you have to, and do every one of those steps in that order. Never collect the data first. Make your hypothesis and critical regions first. So until then, we'll see you in the next one.